I think we're probably ready to start now. So welcome everybody to the second fully virtual Helsinki Data Science Meetup. We used to have in the old world these face-to-face, but we're really happy to see so many of you here joining us virtually. And today Helsinki Data Meetup will be going energy. So we have Helen as our host, and we will be hearing about some very cool use cases there. So this is the agenda now. So Saara Hyvönen from DAIN Studios here talking now, a couple of opening words, and then I will give the stage to Mikko Muurinen from Helen, who will tell about data and AI at Helen, and that will be followed by a series of other presentations on different kind of use cases around data and AI and machine learning at Helen. Each presentation will run approximately 15 minutes. We'll hopefully around 5 minutes, then time for questions. So, and we will be monitoring the Q&A as well. Some more details on that in a couple of slides. But feel free to kind of participate and ask around the questions. And we will be closing around 7:30. And just to introduce who are we, or who is DAIN Studios. So we're a data and AI company working around all kinds of data AI related things from data and AI strategies to actual execution, machine learning models, you name it. We are operating in three studios in Helsinki, Berlin, and Munich, and are currently around 30 data experts. Main business model is consulting across industries, across countries, but with data and AI in the core. We're also working on some very preliminary product ideas around XAI and customer care AI. And we're also kind of named as one of the most interesting players in the AI community here among the 5 AI consultancies on the list by Teknologiateollisuus. So we're in good company. And a few words about the Helsinki Data Science Meetup. So as many of you already know, you have probably participated in several meetups already. Welcome to the newcomers in any case. This is a forum that brings together people who are interested in data science and AI. We've been facilitating these since 2016. These meetups have been hosted by companies that are active in data and AI. And we've heard about kind of fascinating cases across a wide range of industries. We have a pool, I think currently around 1,200 data enthusiasts who somehow participate in these meetups. So if some of you are interested in hosting a next meetup, then please reach out to us. Some kind of house rule now. So please be kind, be inclusive, and be curious. So feel free to participate in the discussions. We have more than 300 people registered into this meetup. So just to make things simple, you're all muted. But if you have questions, please place them in the Q&A box during or after the presentation, and we'll be picking up questions from there. So myself and other moderators here. Please follow us on LinkedIn and Twitter, and feel free to tweet yourself or update. Should you have connection issues, there's a chat feed, so please, any technical problems or other topics like that, please use the chat for that. I will be giving the scene in a moment to Mikko, but before that, I think that we would like to have a little poll to see where we are all coming from. So, Tizian, if you may.
I started the poll now. I will close it as soon as we have reached 90 or something, but just to give you a gist, most of the people are data scientists, 40% right now, 7% data engineering, 10% business intelligence, and 20% business functions, and 22% others. Slight focus on data science, but also business functions and others are roughly a fifth of the
Excellent.
visitors.
Okay, so without further ado, this is useful input also for our presenters to know who they're talking to. I will stop sharing and give the floor to Mikko.
Yeah, thank you. I'll try to share the screen as well. Yeah, probably now you can see the presentation. If not, then someone shout. Okay, thank you, DAIN, for having us here at the Helsinki Data Science Meetup. We're happy to host the meeting and tell you more about our plans and our solutions that we have already been working on. It's nice to meet so many data and AI enthusiastic people who are as interested in this subject as we are. And please feel free to ask anything about our plans and our presentations. We have a divided work so that the one who is not presenting at the moment, those people can answer those questions already in the Q&A, even within the presentation, and then afterwards all the open questions we try to answer as quickly as possible in the Q&A period, and also afterwards we can fill in the rest of the questions that we are not able to answer in the couple of minutes that we are reserving after each presentation. So my name is Mikko Muurinen. I'm the head of data and AI at Helen. I've been with the company since May, so only half a year yet, but my background is from the beginning of this century. So I've been doing data related stuff for a bit over 20 years, and I've been working both in the IT and the business side, also in the public sector and in private sector, in smaller companies, small startups and bigger multinational companies, and also been on the vendor side and on the buyer side. So I know the pains of the BI and data and AI vendors as well. But now at the customer side at Helen, and I'll walk you through the main brief points of Helen, and then focus more on the AI side and data side. What are the use cases that we have recognized? What is AI? What does data and AI mean at Helen? What are the plans and what are the steps that we are taking? And after that, our data scientists and analyst Erno will tell you more about the practical use cases, projects we have been doing, and plans and POCs and trials we are currently doing and have been doing for the past couple of months. Okay, briefly about Helen. We are quite an old company based in Helsinki. Used to be the electricity company of city of Helsinki, and from the origins, from 1909, we have been focusing on the environment. The reason that this company was founded was to clean up the air in the city of Helsinki, where everyone was burning their own wood ovens and wood stoves, and heating up their houses by themselves. So this electricity company and heating company was founded so that the people of Helsinki could move into more environmental friendly heating and energy solutions. So we are still using a lot of coal, and that's a bad thing. But we have quite ambitious goals to be carbon neutral by 2035, and we have been taking steps already for quite a long time, and we have steps to lower the coal dependency even in next couple of years. We are, if we would be a software company, we would be like a full stack house. So we are doing everything in this energy sector. We are producing the energy, district heating, district cooling, electricity. We are also selling and trading the energy. We are distributing the energy to our customers, and also we are maintaining the distribution networks. So there are some key figures that you can see on the slides, but the main thing is that we are we have very secure and capable networks. That there's only approximately 1.5 minutes per by average the time that there's no electricity per year per customer. So very high performing networks, and we can supply the electricity very securely. So what does this energy sector mean for data and AI? We are lucky to be in a company that recognizes the importance of data and AI and analytics in their business. We have a good support from all of our directors, the board of directors, and the data and analytics and AI has been recognized as one of the key strategic capabilities and competencies in the company. So we have been building our capabilities and our data strategies recently, and data is in the center of all of our work. So we recognize that everything that we do creates data, and it will be created even more quickly and more rapidly in the future. There are more and more places where the data comes from, and there are a lot of new use cases for using data and AI in the future. In our new data strategy, I will tell you a little bit more about the data strategy after a few slides, but in our new data strategy, we have recognized this or lifted this slogan, Helen loves data, as our North Star or slogan. So it means that we need to take care of the data, nurture it, keep it in good condition, take care that it's handled responsibly, it's gathered responsibly, and it's gathered from all of the places. And if we do keep good care of our data, the data will love us back. So it will give us benefits, business benefits, and competitive advantage even. And our data strategy doesn't say that the data and AI unit or analytics team or data science team loves data. It's Helen loves data. So it's all of the company is involved in this data strategy. So what does AI mean for us? This is a slide that shows Helen's journey to carbon neutrality, and it shows the current solutions, how we produce energy, how we distribute it, what kind of additional services we provide under this road that goes through the middle. And it also shows the new solutions that we are building to become carbon neutral. And AI fits in all of these places. If we would draw all of the AI use cases and data use cases, we would not see this picture, but I have put a couple of examples where we are using AI and where we are planning to use AI. As a matter of fact, I had a meeting last week with our board of directors, and I told them that my vision and our vision is that Helen is powered by AI in sometime in the future, and that is due to a couple of facts. One is that we are becoming more and more customer centric, and we want to provide customer care tailored to each customer. So as we have roughly a bit over 500,000 customers currently, there's no way that we could do that manually or with manpower. So we need AI to do that, and automation and analytics to do that. And on the other hand, we are moving into more distributed energy system. So instead of three big coal plants, we are moving into a world where we have solar plants, solar farms, wind farms. We are taking energy from wastewater. We are trying new types of energy forms as well, bioenergy, so on. And the three data points that provide currently most of our production data will become 10,000 points or 100,000 points, because each solar plant, solar panel even has their own IoT sensors which produce data every second. And we are also moving into more into smart buildings, smart living, smart traffic, and all of those areas provide a lot of data that we need to analyze. And there's no way that a human or even an army of humans can handle that kind of energy system or optimize or even drive that kind of energy system. So it needs to be AI driven. So a couple of use cases could be, if I can change these slides. So I renamed this Helen's AI Road to Carbon Neutrality. We are also already doing some of these things. Some of them are just plans for the future. Sami, Erno, and Juha will tell you more in the detail about most of these. But it's about predicting energy consumptions, how our consumers and customers are using the energy, how businesses and companies are using energy, how much we can produce, for example, solar power or wind power, what is the optimal placement of our chargers for the electric transport vehicles, where in our network we have leaks or anomalies, so we could more quickly identify those problematic places and save on the cost and lower the wastes. It's optimizing the waste energy, as we are finding the new ways of gathering energy from, for example, wastewater. So we want to optimize how much we can get energy out of different sources. It's about process automation, how well our power plants are running, when is the optimal place to optimal time to maintain those plants, what is the most optimal fuel ratio or something like that. It's about the energy trading. There's a big potential in being the best trader in the energy markets. It's about hedging. It's about predictive maintenance, how we can find out components that are failing, how we can predict which parts of the electrical grid or district heating grid is having malfunctions. And it's about the customers, how we segment the customers, how we target advertising, how we improve sales for those customer segments. It's about lowering customer churn. That's a good use case for AI as well. The energy sector is quite, there's not much customer loyalty. So we are, of course, like any other energy business, in trying to find out how we can keep those customers. And there's more and more competition especially in the electricity side. The companies that we are competing are trying new ways to get our customers from us. It's about cross-selling. We are developing these new products to enhance our traditional sales, like new energy consulting, new power, solar power, and smart grid capabilities, and so on. It's about dynamic pricing. It's about getting quiet signals from customer communication, from emails, from phone calls, from feedbacks. And it's about also using this in HR, improving the employee performance and retention, targeting trainings, and so on. And for example, motion detection, smoke detection could be improving our security in the power plants and in the sites. And also bringing this to the customer and their homes and their locations, improving their conditions, finding the best ways to heat the house, and the most energy efficient ways to use the energy, find the cheapest hours of the time to heat up the house, and for example, use the water heating as a battery. And also in the back office side, it's about optimal procurement. We are buying a lot of stuff, especially fuel, how we can most optimally buy that fuel. It's about back office process automation, whether it's in finance or HR or marketing or sales. And it's about risks and information security. Information security is one good use case for AI. There are more and more threats out there, and using security solutions that utilize AI is one of the key areas. I'm not going to go so deeply into the data strategy. We are leaving time for the other speakers, but we renewed our data strategy. Here are some key points. You can get those slides after our presentation from the website, so you can look at what are the key points in the data strategy. But we are expanding the use of data and analytics and AI to all of the people in Helen ecosystem, even outside the company, to partners, customers, society. And we are using modern technologies and new kinds of organizational capabilities. We are trying to be more flexible, trying to be more creative and innovative with the business side. We are trying new types of collaboration models. We have been creating these virtual teams that we call tribes to improve the collaboration with the business side, and including data engineers, data scientists, data analysts, and data governance experts in the same discussion with the business, so we can get full benefit of our cross team experts. And of course, this is not isolated. This is connected to our customer platforms, our ICT platforms, how we connect to our partners, but most importantly, how we connect to our all of the sensors and IoT machines that are out there. And all of these areas are expanding the use cases for data and AI platform. Data and AI is not an isolated island. It's a way to connect all of these other platforms to work as a glue or even as a lubricant to distribute the benefits from example, using partner solutions and using our internal data and also data from IoT platforms and create something new for the customers. And we can distribute that, for example, through our mobile apps or our websites. And data and AI is in the center of this.
Yeah, Mikko, we're out of time, unfortunately.
Yeah, this was the last slide. So
excellent. So I'll just combine two questions into one before moving onward. So there are a couple of questions in the Q&A. So does not AI create complexity for network planners by producing huge data? Also managing cybersecurity would be a challenge in the future. Can you give a 15-second?
Maybe I'll answer that in the Q&A while the next presentations are running. I'll write something down there.
Okay, excellent.
Yep.
Thank you.
Thank you. Now we are moving to Sami's presentation.
Hello. I'm Sami Kojola, a freshly minted data scientist from the freshly minted Helen Data Science team. And I'm going to be talking to you about one of the use cases you saw on Mikko's larger roadmap. So short-term forecasting in production. So we're tackling a quite specific business problem on what kind of forecasting an energy company needs to do to run the production assets we have in an optimal way. So here is a high-level picture of the problem we're trying to solve with forecasting. So on the upper right-hand corner, we have a production mix we need to optimize. The sum total sums up to the load in electricity, heating, and cooling we need to achieve. So we need to have good forecasts on the level we need to be producing at each hour and in the future in a 15-minute intervals when the Nordics are moving into 15 minutes control periods in the electricity market. So our load forecasting defines the level we need to reach in each time step. And then we have marginally cheap renewable production, which fills some part of that, which we don't have a good control over. It fills some part of it, and then the rest needs to be produced with the assets we control. So burning coal or using hydro or using gas, basically. And what is the optimal combination of those? What is the optimal ramp-up time of those production facilities? What are the optimal ramp-down times of those facilities so that we can meet the difference between load and the cheap variable resources is defined by prices. So in Helsinki, as in many other places in Finland, we use a lot of combined heat and power production. So the same process produces both heat and electricity. And depending on our price forecasts, we select a different production mix so that when electricity is expensive, we get more electricity from the production mix, and when it's cheaper, we can buy the electricity from the market and produce less electricity from the heat production. So optimizing that whole machinery requires a lot of forecasting, and we've done machine learning forecasts in all of these areas. Couple are in production, one is in testing right now. And going into why machine learning here? Well, basically, with machine learning, we can use larger data sets and get better estimates for the weak signals. So we get wider data sets from the things that are affecting our production or load or prices, and there are more signals there, and we get a longer data set, and we can estimate those weak signals more precisely. I like this picture on the right by Siilasmaa from Nokia, Kristo Siilasmaa, with traditional regression methods we've been using before. You hit a certain threshold after which adding more data doesn't produce more accurate results, but using more complicated newer methodologies, we can utilize the large sets of data we have and get better forecasts. So basically, I think this comes from the development of computing. Storage is cheaper, computation is cheaper. We have good new algorithms with which we can do forecasting better. And also in our case, some of the forecasts have been done with human input. Human is choosing the right weather forecast, is choosing the right models, but with just giving the data to a bit more complicated algorithm, the machine can do the decisions and weight the factors by itself, so no human input is needed in forecasting these things anymore. And in case of heat load forecasting, what are these wider sets of data that we've utilized to get better predictions on heat consumption? So in my conceptualization, heat consumption comes from two factors. We have the weather, how cold it is outside, how much we need to heat the buildings. Wind has some effect for cooling the buildings, and then solar radiation. And then there is the human factor, how people are home or in the office, how hot are they keeping their homes, etc. So on the weather side, we are now utilizing wider sets of weather data, having more weather stations, more forecasts being utilized better to get a better picture of what are the actual weather conditions around the city. And then we are using production and transmission data from our production network to get a real-time signal on what is the actual heat consumption, because we are not getting the actual heat consumption measurements right now in a real-time way. There is a several day lag on getting the data we actually charge people for. So the production and the transmission congestion data is used in the model to estimate where are we now in the heat consumption, and that is very important for the short-term forecasting. A bit about weather data. So Helsinki is a large area, and our network covers most of the city. So there are different weather conditions around the city, in the north, in the south, center, in the east, near the coast. So including more weather stations, we are achieving better accuracy in forecasting. Here we can see on the right that after including three weather stations, we are not improving the accuracy that much, but that might be because also already with 3 weather stations with temperature, wind speed, and wind direction, we are getting a good picture on the probable temperature gradient around the city. Then about what kind of technologies we've used thus far. So I like to use Python. My team leader prefers R. You can discuss that in the comments. But in modeling, pretty basic Keras, TensorFlow, XGBoost. Then in validation and looking at the data, pretty basic Python data stack. We've used Docker to put the models in containers, used RabbitMQ as the message broker from the production data systems, and then deployed the models with Docker Compose. We also have the forecast accuracy being watched with Power BI, so that I don't need to always be making graphs on the forecast accuracy with Python, but the business and the system operators can look at the forecasting accuracies on different dimensions by themselves. And if you hear a bit about the results we've gotten with different forecasts. So in the heat consumption space, the biggest improvement has been on short-term intraday forecasting, mostly because the inclusion of the estimation of consumption in the forecast is so relevant. So we've deployed a model in production from mid-June. So until today, we've gotten around 25% improvement in accuracy in the 1 to 6 hour scope. Running on a year-long set of test data, we are estimating that we get around 20% improvement in accuracy in that space. Here on the lower left-hand corner, we have a bit of graphs on another forecasting model that's running on production. We're forecasting the wastewater energy we get. So that goes into variable resource space. And here I'm comparing a baseline that's an optimized balancing of the previous day's wastewater flow to a regression 1, which is a more traditional time series regression, to what you would call a machine learning regression. So here again, the area is large where the wastewater comes from Sipoo to Mäntsälä. So we are incorporating a wide set. It's saying that my internet connection is unstable.
Yeah, we lost you for a moment, but now we hear you again. So
to have a data science team that is well integrated with the business and the system operators, so that the data science team and the operators can together define what is being measured and what is being stored, because the company data is what makes this work valuable. We're probably all basically using the same forecasting frameworks made by the open source community or large American tech firms, but for a company, the competitive advantage comes from the set of data that the people working with the assets and the data scientist team define to be measured and stored. In closing, time series forecasting and optimization are a big part of an energy company's daily and hourly operations. Machine learning can help utilize large data sets, providing more accurate forecasts for core inputs, and also help forecast things that were not forecastable before. Also, there are labor savings versus manual forecasting of these inputs. And as a last word, I want to say that data science is a company effort. Statistical modeling is not a competitive advantage for the average firm, but the company data you have can be.
Thank you, Sami. I think there is some time for a couple of questions if you're up to it. We have quite a few, and some of them have already been answered here, but just looking at the top of the list, how does the situation of Corona and higher home times affect heat loads? Any difference? Does the model react to the change?
Yeah, the difference is smaller than one might suspect, but we've achieved good results with the during the Corona time also. I think the model has adapted to that quite well.
Excellent. And then there's a question around, to what extent does your algorithm consider edge cases? In other words, in addition to accuracy predicting expected demands, a system operator might be more concerned to have sufficient capacity to cover an outlier event.
To some extent. So we've done a bunch of error handling in the model for situations where the network, for example, is not working properly. So there is logic done for those kind of situations. But when sometimes there comes situations where things just break down, that's when humans take hold of the production network and the algorithms cannot function. Always when you're developing a system, there are cases where things break down in a way that you cannot suspect. We've incorporated cases that we've seen historically how the data breaks down, basically.
Then, since we still have time for a couple more, which metrics do you use for model evaluation?
Basically, mean absolute error, the autocorrelation of the error, so that we're not consistently wrong in the same direction, maximum, minimum errors. Those are basically what we're looking at.
And how are the model results utilized in practice? Are there some power sources actually ramped up or down?
Yeah, basically the model results go into our optimization machine, which tells which production facilities should be ramped up or down and at which time. So basically there is the optimization part, which pulls together all of these forecasts and does the optimization over time, what should be done with the assets. So these results go into that calculation.
And then what kind of edge/IoT devices do you need to use?
Basically, I don't know, do you call it IoT, but we have measurements in the network, in the heating network, what are the pressures in the pipes, what is the energy being put into the pipes. So basically, those are the measurement data coming from the heating network that are used to estimate the consumption.
Yeah, other types of edge and IoT devices, of course, in the other sides of the business are related to the smart houses and smart living devices that monitor the environmental or the conditions inside houses and buildings. Also IoT devices that are related to the smart traffic or smart vehicles, for example, to those charging stations and so on. And of course, all the solar panels have IoT devices, so we can control them and shut them down and turn them up and do configurations. And of course, wind power plants and wind farms also have tons of IoT devices in those big windmills. So okay. There are a lot of edge cases. We are maybe in the beginning. We have a lot of sensors, but currently they are all dependent on the vendors. But we are trying to create some kind of IoT IoT platform that combines all of the different sensors and unifies the information that we have from all of those sensors.
Excellent. So thank you, Sami, and it's time to move forward to Erno. There are still some questions remaining in the Q&A, but the Helen team has been doing a great job in answering them there. So let's continue with the program, and you can keep an eye on the Q&A then separately. Thank you.
Hello everybody. My name is Erno Savela, working here at Helen as a development manager and team lead, and also trying to use some of my mathematics skills sometimes to solve a couple of problems too. So the topic today is forecasting long-term electricity demand for hedging and residential sector in Finland. So what is this all about? Pretty much we have that 500,000 customers, and most of those or many of those have fixed term contracts. So you buy electricity for 1-2 years for a certain price. Well, the thing is that we need to obviously hedge that. So we need to already buy futures from the electricity market, and that's how we can run this business. And to do that, we need to forecast how much these customers consume electricity. And this is quite interesting thing in the sense that we talk here definitely over 100 million euros is definitely the amounts we are hedging here. So anybody can calculate that if you multiply electricity bills with 500,000 customers, it comes like a big number. Okay, so what we talk in more detail is the development process and results, so how this forecasting is being made, and then we a little bit talk why we don't use a commercial alternative. But let's start with a small theory here. So the law of large numbers. I was actually watching Netflix not that long time ago, and Ozark is one good series there, and there is Marty named guy running a little casino operation, and here's a good quote. So if we think about one person making one bet, we cannot possibly tell what this person is going to do. But the thing is that the law of large numbers tells me that 1 million people making 1 million bet, that's completely predictable, completely ordered. Ja sitten and then Marty continues that you know that if we have 1 million people walking here, I can tell 3% try to cheat us, another 1.2% will be here to try to catch us committing a crime. And the thing is that, you know, when we have a lot of people, a lot of mass, things come predictable. And actually now when we have a little bit of surveillance and a little bit of time, we can find some patterns, and now everybody can already start to think that, let's say that we now forecast the electricity demand for the next summer. How well we know it? What is actually the accuracy we can know? How well we can know how much our customers consume electricity next summer? How well we'll know it now? I don't tell it yet, but I will tell it later. Okay. So then let's go to the development process and results. So here are a couple of key factors listed what come into play when we start to trying to hedge a little bit of electricity here for long term. So first of all is science. So the most important part came in the previous slide from a TV series. Then the second part is temperature. So all who have been in physics classes understand a little bit the relationship between energy and temperature. So yeah, there is a linear relationship, high correlation to temperature and its aggregates when we think about electricity consumption. And this applies especially in the heating period, obviously. And there are some seasonal differences and so on, but anyways. Then the business side is that the thing is that we need to do this forecast for a couple of different things too. So actually, in addition to hedging the electricity, itself. We need to hedge our product sources. So does it come from solar or water or wind and so on? So what the consumers are buying, because we need to buy those certificates. Then we need to make different kind of financial forecasting and budgeting. It all comes also from this modeling. So okay, there are some goals by the management, but anyways. And then split to the key factors means that once we know the science and business, it's good to start to think a little bit what we actually want to do here. So the basic structure here of the modeling is that we need to know the number of consumption sites we have. We need to know how much each consumption site consumes electricity. And we need to then, of course, hedge this all. So we need to think a little bit the hedging levels and the hedging period. And then we need to a little bit think that, well, once we know what we want to do, we want to know how we measure the success in it, what we are doing. So we want to minimize the financial risk. We are looking to reliability, maintainability, explainable changes. The thing is that this is like so big money here that 1% is always like multiple million or can be like big money. So it comes to risk management also in terms of the model and data. Then forecasting and calculating the number of consumption sites is important. And here the success measure, the most important one we use for the forecast model is mean absolute percentage error for the non-extreme months in weather per consumption site. So the thing is here that we try to estimate here how much is this kind of most average consumption in the future. We potentially cannot know what is the most extreme or minimum or whatever between. We need to forecast here this kind of most average, and therefore the model itself should be good in that job, not necessarily forecasting the minimum or maximum. Then it's good to have a couple of models. So in this case, we had our own old model, then a commercial product, and multiple own models. In the end, we choose then this kind of linear +3 modeling alternative because it fits to this, well, relatively simple setup. In the end, we try to here forecast the average or typical, not necessarily the maximum or minimum like in the production setup, what Sami was talking about. And then there is the follow-up part. So it goes really deeply to the data management quality and so on. The actual model actually works really stable. It's more has to do all with the data. So then some results. So if you now were thinking that, well, how well we know these things, so how well we know how much we consume this electricity. The thing is that we made a model actually last autumn. And here are the results, how it now looks when we look the actual results for each month. So in last autumn, we couldn't possibly know how cold or warm the winter is, and we couldn't know there is corona and whatever. This actually includes both now, also small businesses are hedged with this same model now. So, but anyhow, if we know the temperature, our mean average or mean error is somewhere like 1.6%, 0.5%. It's somewhere around 2% to be precise, if we know how the weather is. So here actually in the lower part are the weather bars. They kind of tell how well we match the weather. So the black one is what is actual, and then the yellow one is what we kind of were predicting. So you can see that when we hit the weather, what we were forecasting, our error is really small, like somewhere 1-2% in the summer, 2%. Actually with the same consumption sites, as there is changing the consumption sites all the time and so on. New customers come and old go. So it would be even 1% if it would be the same sites, but with new sites, okay, 2%. Then what comes to the winter, it gets of course a little bit difficult here with some 15% error, so on, because the thing is that we just cannot really know how the weather is, and then there's this linear correlation to the energy consumption, and that's then that. But anyway, we do the best we can. Yeah. Then a little bit about the commercial alternative. So this is actually more interesting because we start to compare some models here. So the thing is that there was a commercial alternative. Not surprising. I mean, we talk about here about big monies. So of course there are companies who try to make better forecasts and models and tools and so on. And of course we also look around those things all the time and like to test them also if they are enough promising. And in this case we also tested one. And the thing is that the science part was a little bit tricky in the sense that we didn't have kind of enough data. So this commercial model, it wanted to do segmentation, and the problem there was that for that segmentation we would have like needed more good data. There was not that kind of stuff available, especially not from the new customers, because we don't know anything about them, not too much at least. And that's why it didn't work that well, the segmentation part. Then a second thing what was a little bit tricky with this commercial model was that it approached things kind of from our daily level. And when we have now studied these things, it seems that that's quite ambitious for the long-term view, or a little bit like complicated. Because the thing is that when you go to the short-term view, you need to start to pay a lot more attention to the feature engineering and the weather patterns and the country and so on. It's not that simple. When you take longer periods of time, things kind of even out more. So you don't need to be so complicated in your stuff. Otherwise, you just get a lot of variance when you try to go too into detail without really understanding what happens. Then what comes to the business side, this commercial model was kind of sensitive. I guess there was the segmentation part especially. So then these things, forecast and whatever, changed a lot, and we couldn't kind of get it why. And then the measurement of success, well, it had a higher error rate, so that was a challenge. And then, well, it might have been better for forecasting maybe min or max, as it was some kind of gradient boosting, to my understanding, the model. So yeah, it might be better for getting the min or max, this type of methodology. Then split to key factors. Well, the thing is that this kind of commercial thing was good only for the thing it did, so the forecasting. But the thing is that actually we like to include a lot of factors in multiple stages. So here was the hedging, here was the forecasting, here was the number of the consumption sites. You need to get all right. It's not enough that you forecast energy right. You need to get right every single step in this thing. And the failure is actually more likely to happen somewhere else than in the forecasting. And in that sense, it's really great to have the data capabilities here at Helen and really develop these things, because the risk lies there in the data, not actually so much in the model itself. Then if we think about the follow-up, also there, the data quality, capabilities, and reporting, they are really maintainable here in-house, so we can really here take things forward and do continuous development. Okay, that was pretty much the content of the presentation. So now there might be still a little bit time for discussion or so.
Thank you, Erno. There's one question on the Q&A. Are you using probabilistic networks to get an estimation of the uncertainty?
No, we are not using that kind of methodology.
As there are no other questions, shall we then move forward to Juha's presentation?
Okay. Is my hair right?
It's great.
Great, thanks. Next tricky thing is if I get this screen sharing to come from the right screen. Okay, right. So I'm Juha Riissanen. I've been with Helen since December 2018. So I'm a long-time veteran. And then before that, I was working in telecommunications, doing all kinds of software development, apart from sales and then quality and process management and analytics. I guess I can just continue and dive into the presentation. So basically, talking about the things that I have done and experienced and contributed during the almost 2 years at Helen in this unit. Okay, so basically Helen has many different business areas and needs, like generating and delivering heat and cold in Helsinki, generating electricity. We have new solutions like solar panels, charging and stuff. Then there is the Helen Venture, looking for startups and those kind of things. So that gives plenty of opportunities to work with various interesting challenges. So broadly, what I've been doing could be classified into three groups. So basically doing data science stuff, doing some kind of internal consultancy and training, and then the rest related in a way or another. In this data science stuff, I've been working in the domains of indoors environment measurements, hydropower, district heating, and some customer segmentation and marketing stuff, to name a few. And with this data science stuff, I mean things where we start from framing the problem with the involved people, finding, getting, wrangling the data, getting it into a useful format, exploring, plotting, characterizing the data, and then creating models and statistical analysis as needed and fit the problem, until we get the product or a report or thing that was expected, or get something that was not expected but still useful. And the tool set that's most familiar to me, you can see on the icons on the right hand side. And even though Sami said that I like R more, I know something about Python as well, but I think things are easier in R anyway. Never mind, I'll be learning Python. Yes, these internal consultancy and training things, we have internal training for Data Academy, educating personnel on the proper use and value of data and how it can be used in businesses. And then we have this ventures arm who are chasing startups, and there every now and then, pretty often actually, there are these claims that they are using AI or machine learning, and that saves the world and things like that. And in that consultancy, me and Sami and others are heavily involved, just like in that internal training activity as well. And then there are these related things, out of which I'd like to pick development of data sharing platform, where we intend to share Helen data with our partners, and also with general public, the part that can be made open, and media. And as pointed out in the Q&A answers already, we are making big moves now from largely Helen internal data systems for data science to using cloud in Azure, and that is taking some non-trivial time slides from my end and from Sami's and others' time. Helen is in the business of power business, and we are generating electricity using power plants in Helsinki in this combined heat and power system, but we get cooling from there as well. We produce electricity using solar farms around Helsinki and increasingly at wind farms in various locations around Finland. And in general, this share of a new energy, especially this wind, is increasing a lot, and this is making it difficult to, or let's say challenging, to keep the grid frequency at 50 Hz for which it has been designed, so that it works without problems to the grid and to the devices and machines that are connected to that. In the old days, the frequency was stable because there were these big rolling machines, turbines and stuff, which had enormous inertia, which ensured that the frequency was at the 50 Hz range. But now with these new electricity sources, there are these rapid fluctuations, and Fingrid, which is managing the grid, is buying reserve capacity from various power plants to be able to rapidly compensate these frequency anomalies. And when hydropower is used in this context, then the direction of, let's say, the Fingrid control requires that it answers rapidly to those changes. And now these hydropower systems, they have been designed to work at that kind of fixed power output, so they are not designed to be so that the speed is changed rapidly, and making the changes rapidly, it means that these heavy parts of the machinery, they have to do much more work than they were designed for, and therefore it also causes load, which is then risking breaking those things. So maintenance costs will rise. So therefore we have been studying with one of our partner how we could buffer these rapid changes, so that we could use a battery there, a big battery that could handle these more rapid changes. And then in that there were measurements done at the hydropower plant, and then I used those measurements and Fingrid historical data to model and estimate the cost and benefit against different battery parameters over time to come up with some numbers how that could be done. And in that I've used the tool set basically here. So Sami, have a look. Python is mentioned. Okay, and this XGBoost was used there as well. There will be a new measurement later this year in that hydropower plant, and I'm kind of anxious to find out how close or far my calculations are. Another snippet of the work. Winters in Helsinki are not always as warm as they seem to have become. So Helen is supplying most of Helsinki buildings with heat through district heating network, and that heat is delivered from these power plants through this district heating network into the buildings, and then there is this heat exchanger, and at that heat exchanger that heat gets transferred to the heating circulation of the building and also to the warm water circulation of the building. And these heat exchangers, they are typically robust and they don't break often, but sometimes they do. And they can break in different ways. The easy way is that let's say the easy to detect is if this district heating water gets kind of into this warm water circulation, then the people living in that house, they typically report back very rapidly that, hey, there's some funny color in the water, do something. So that's easy to detect. But then if that heat exchanger leaks to the other side, so this fresh water gets to the district heating network, that's much harder to detect because it's all encapsulated in pipes and enclosures. But it will cause some effects. One effect is that the water is more oxygenated than the district heating water, so it will corrode these pipes. So that's in the interest of Helen to find these leaks rather sooner than later. But then, of course, if the water leaks to that pipe, then the water bill for that building will increase. And also, if and when that water leaks to this district heating pipe, then the kind of measurements based on which the bill is calculated, the district heating bill is calculated, that might increase because the difference of temperature between in and out is larger than it was supposed to be. Okay, so basically what I've done is I've done a prototype where I modeled for basically for each of these buildings the normal consumption of district heat, taking into account the history of the building and then weather and time of year, and basically the model then makes a prediction how the heat should have been consumed over the past several days. So here you might see this prediction for this one site, and then there is this measured consumption, this blue line. So basically, when these two differ too much, then it can raise a flag that, hey, there is some fishy, something needs to be investigated. This is intended, or the vision for this prototype has been to be a microservice that can then be used by different Helen services or products to identify this kind of issues. And it has been a nice playground of different technologies and methods to work with. One challenge for this model is that there are no two buildings with similar consumption profile, and these change. So it's easy to get false positives. So there is some nice, interesting work to be done for this model later on. I had the opportunity to experiment with the customer segmentation. There were some early marketing experiments where we had some idea about customers that were interested in certain products and who were not interested in certain products, and then created two different messages. So we had basically 4 groups of people whose behavior, basically buying behavior, or we tracked and found out that our idea of this population was wrong. At least both populations, they were very much similar regarding how they interacted with the offering, but then the sales pitch was slightly better. One of the sales pitch was slightly better than the other. So there we used these open data and also Helen data. I found out that reusing software is the blessing, and I've been doing a few R packages for internal usage, and there are, if interested, there is a link to a document where there are some nice starting suggestions how to move with R and Python. But I guess I've used my time, so this basically was the presentation. Thank you. Sorry about having to rush the 2 last slides a little bit too quickly, but you'll get the slides.
Thank you, Juha. There is a question. Have you published your model for heat exchangers?
Well, unfortunately, or fortunately in the sense that it's not polished. Unfortunately, because I think I'm not allowed, because we are in that business.
There was another question that I primarily answered, prematurely answered, that you had confidence bands in the heat exchange estimates, yes, but you were using XGBoost. At least the original package does not have the mathematics to estimate quantiles or confidence intervals. How did you do that?
I don't remember now the details, but I think that I sort of faked it so that it's indicating likely error or confidence area, but it's not a strict one. It's kind of indicative.
Then there's a question how big the data set you used was, but I'm actually suspecting that might have been actually for Erno, but I guess maybe you or Erno can give an indication on what the size of the data is you're working with.
These data sets I've used for this anomaly stuff, they were hourly data, and basically for a building, I've used 4 or 5 years worth of data.
The commercial product used a data set which had like every hour of every consumption site we have, so quite a many million rows of data, and then also like super much weather stations and hourly weather data, and the whole model was training maybe like whole night and whatever, and still the results were what they were. And actually this more simple model, what we now use, gives better results and runs in 4 seconds, and it doesn't use that much data. No, it's more the data engineering which makes things work.
Excellent. Hey, thank you, Juha, thank you, Erno, thank you, Mikko, and thank you, Sami, for your excellent presentations. And for the information of everyone, there was already some discussion on chat, but we will share the slides and the recording that was made on this via email next week later on. And once we close this webinar, there will be a poll still asking your opinion on kind of future topics, but not all is free because we have our next Data Science Meetup coming up early next year. It will be hosted by CSC, so the Center for Scientific Computing. For those who don't know CSC already, it's a non-profit state enterprise which provides these high-quality IT services traditionally more for universities and research institutes and so forth, but in the future increasingly also for enterprises. And they will be especially telling about Lumi, which is a new supercomputing platform for AI, and be telling about some opportunities also for enterprises there, but also about some of the machine learning cases that have been run there on. So stay tuned for more information on that. Mikko, do you have some closing words? I really want to thank you and all of you guys. This was super interesting, and we were excellent at timekeeping.
Yeah, thank you for having us, and thank you for all the attendees and for good questions and lively commenting. So it was nice to meet so many people. It would have been even nicer to meet face to face, but now during this time, this was an excellent way to spread our story to you.
Okay, so thank you everybody, and have a good evening and good rest of the week. See you next year.